Hey folks, we're gonna be looking at mirrors and lenses today. A lot of the mathematics behind how light behaves, but also taking a look at how to draw how light behaves when it interacts with a mirror or lens. We have quite a few things already written down, and so we're going to be going through some key points and preliminary things before we get into any of the math or drawing. So, first and foremost, I have labeled here the principal axis. This is the thing that kind of runs through the center of the mirror or lens and perpendicular to the mirror itself. Next up, we have C for the center of curvature. So if we imagine the mirror to be not just a section, but a whole sphere, this may be where the center is. So center of curvature. And what goes with that is the R value or radius, which is the distance from the center to the mirror itself. Next up, we have focal point. This is labeled capital F, and then you have a cursive or lowercase f for focal length. So you have focal point and focal length. These are so much one and the same that often I just forget about the capitalized version. But as a concept, the focal point is kind of where all the light will converge through how the mirror deflects it. And focal length is actually that distance away from the mirror. So there's your cursive F. And then finally, V is our vertex. So this point here represents a vertex. Okay, so that's quite a bit. Just talking a little further about this, we have one equation that we can already kind of look at, and that's that F is equal to R divided by 2. So the radius divided by 2 will give us our focal length. Okay, now we want to move into the mirror equation and sign conventions. And hopefully a lot of this writing here will make a little more sense once we actually have our mirror equation. For me, there really is, there's a mirror equation, and then it also applies to lenses. Almost everything that we're going to talk about here in terms of mirrors is the same for lenses. So mirror equation looks like this. 1 over the object distance plus 1 over the image distance is going to be equal to 1 over the focal length. So this is how far away the object is. This is how far away the image of the object will be. And this is our focal length of the mirror or lens. So that's our first big equation. And that really is the mirror equation. But I like to include the last piece, which has to do with magnification. The magnification, or how much bigger or smaller our image is compared to our object, is the height of the image divided by the height of the object, or negative image distance divided by object distance. So this is one big equivalency. Often remember this by hi-ho and di-do. So with these two equations, we have a sign convention for quantities that are going to be positive or negative. And it kind of looks a little bit like this. Real objects and images will have a positive distance, whereas virtual objects and images will have a negative distance. Upright images and objects will have a positive height, and inverted images and objects will have a negative height. Also, for both mirrors and lenses, if it is a converging mirror, the focal length, I don't know if you can see that, but the focal length will be greater than 0, or it will be positive. If it's a diverging mirror, the focal length will be less than 0, and therefore negative. Okay, so let's actually talk a little bit about what a converging and diverging mirror / lens are. So we'll start with mirrors over here. If our mirror is curved as such and our object appears here, this is a converging mirror. If our mirror is curved like so, and our object appears here, this would be known as a diverging mirror. It's quite similar for lenses. A lens like so is a converging lens. And a diverging lens looks like this. Okay, with the main difference being mirrors completely reflect light and lenses will allow light to pass through. Okay. So with that, let's actually look at some examples. Now I have a converging mirror here, and we want to look at two ways to do this. And the first is by drawing, and when we draw what's going to happen with the light, we have to draw 3 different lines. The first needs to be parallel to the principal axis. The second will go through C. And the third will go through F. Okay, and that's kind of because this is what's going to happen. Due to our law of reflection and a curved mirror, parallel to the principal axis hits the mirror and reflects through the focal point. Through the center, hits the mirror, and bounces completely back in the exact same line. And then finally, through F, is going to hit the mirror and bounce back perpendicular, or parallel to the principal axis. And so all 3 of those lines meet up here, And so our image looks like this compared to our object. Based on this, we can tell a few things. We can say, just by drawing, that our image is real, inverted, and it would seem reduced. So that's just by drawing. Now let's put some numbers into things and actually use our mirror equation to calculate all of these things. So our mirror equation, 1 over the object distance plus 1 over the image distance is equal to 1 over f. Let's say that our focal length is 5 centimeters and our object distance is 12 centimeters and our object height is 6 centimeters. So then our equation becomes this: 1 over 12 plus 1 over the image distance is equal to 1 over 5. And the 5 will be positive because this is a converging mirror. So now we have this equation. We can solve for the image distance. So 1 over image distance will be equal to 1 over 5 minus 1 over 12. And here's how you do that. One over 5 subtract 1 over 12, and that will give you this weird decimal number. That is equal to 1 over the image distance. And I don't really care about that. I just want the image distance, and so I can press a nice little button here, the inverse button, and that will give me 8.57. So our image distance will be 8.57 meters. It comes out to be positive, which tells me that it's a real image. It's also in between the focal length, or the focal point, and the center of curvature, as it is in between 5 and 10. So we get a lot of information from our calculations. Next up, let's do magnification. And we can say that the magnification is hi-ho negative dido. So unless I'm asked for, what is the enlargement or reduction, that would be the ratio between these two things. But what I actually want to find out is what is the image height based on all the other quantities. And I know that this is the equivalency based off of magnification, and we can calculate for that by saying, well, negative sign, our image distance, 8.57 over 12 multiplied by our object height, which was 6. So we get around 4.285 centimeters, and that tells us quite a few things. Also, it's negative 4.285 centimeters. So that tells us it's a smaller image than what the object really is, so it's reduced. And what tells us that it is inverted? Well, if we come back to our sign convention here, the height being less than 0 tells us that it's virtual. And so that will be a virtual image. Sorry. Here's the one we're looking for. Okay. Height being less than 0 tells us that it's an inverted image. Distance being less than 0 would be virtual, which this distance is not. So this distance is positive, so it is real. And its height is negative, which means it is inverted. Just to clear up that. There's a lot of things going on with positives and negatives, and there's a lot of different quantities. It's very easy to get confused. So I always double check with my notes. Okay, well, let's take a look at a diverging lens. And we'll both draw the way the light will refract through this lens, as well as we'll do some math. So to set up for the math, we'll do object distance of 15 centimeters. Focal length will be 5 centimeters once more. And the object height will be 3 centimeters. What's also important to note is that focal length will be negative because this is a diverging lens. And let's draw our lines that we have to draw. Now, most often you have to draw 3. I found here that wasn't quite necessary, and sometimes it turns out that way. So we'll draw our first one parallel, and it goes all the way to the center of the lens. And then this diverging lens spreads light. So the light rays that come in kind of go off like that. And they'll leave a trail back to the focal length. That's how I've always thought of it. And then another ray of light crosses through kind of the vertex of the mirror. And so our object, we can kind of already see it's going to appear right here. Now let's actually use our lens equation and do some calculations. So 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. So we have this. Okay, so let's kind of calculate. We'll just do the whole thing all at once. So 1 over 5 but it's negative, minus 1 over 15, and then inverse. So negative 3.75 centimeters is our image distance. So it comes to be before the focal point, which our drawing tells us, but now so does our math. Our math backs that up as well. Lastly, we have hi-ho, dido. The image height will be negative multiplied by negative 3.75 all over object distance of 15 and object height comes up here for 3. So image height is negative cancels and we end up dividing by 5. So it's 0.75 centimeters and it is positive. So once again, we'll come back to our sign convention. Okay, so distance is negative, so we have a virtual object, or sorry, we have a virtual image, because the image distance is negative. The object distance was positive, it was real. We also have a positive height, so that's upright image, and that's what our drawing also tells us. So these are kind of the main ideas of both mirrors and lenses when it comes to drawing ray diagrams and the mathematical processes that kind of govern how we draw things. I hope that makes sense, and that should be a good start for you guys in drawing and the math behind mirrors and lenses.